Everyone can see a whiteboard, right? Okay. Then
Jared, it's okay. We will later record the meeting, okay? So we will share the recordings with the parents and the students later after this session. So don't worry.
Okay.
okay. Wait, Brian, did you want to share your method? No? Does anyone want to share the method for this problem?
Yeah.
Sure, Jameson.
So this is my method. So you see, it for one, so I'm not sure if I'm correct, but if he plays for one day, is certainly going to win because 101 minus 1 divided by 100 will give us an 100% chance. And in addition, it will give us half a credit, which is a lot compared to future ones. Now, how are we going to figure this out? So we're going to multiply the chances of winning, I think, times the amounts of credits. So clearly we need at least one day, but let's continue. So let's say it's 2 days. That'll be 99 divided by 100 are our odds of winning. But our credit, now, sorry about that. Our credit decreases to a quarter. So this is actually less than having 100% chance times a half. And this here, this is actually less than a quarter. So I believe that optimally it would be one day. Although, of course, I am very likely to be incorrect, as I said.
Okay, so actually the answer is not one day. So as you noticed, on the second day of gambling, you're expected to earn less than the first day. But just because you earn less than the first day doesn't mean that you should stop. So what you should instead think about is compare like your expected winnings versus your expected loss. So the loss comes from the case in which you lose all your money. The winnings come in from the case in which you win your gambling. So you want to compare the loss and winning. And so if you think about it logically, while the expected winning is bigger than the expected loss, you should keep on gambling because you have an expected net profit.
Yes.
So let's calculate for each of these days. I'm gonna scroll down here. Or actually, I'll move this to the side. So let's find a general formula for on the ice day, how much money you're going to make.
Yes.
So could someone tell me how much you're expected to earn? Just like how much you expected to earn, like without factoring in your losses.
Oh, so how
Just like does anyone want to answer? I'm sure probably some of like quite a few of you got this one right. So please like take the time to like answer the problem. No one? Okay. So remember expected winning is the probability that you win multiplied by the amount of money that you get when you win. So this is on day I. First of all, this is expected winning. Now let's talk about the expected loss. So this is wins. As for the loss, the probability that you lose is going to be I minus 1 over 100. And this is plus 1/2 because because suppose that you have won all the way up to this moment. Let me let them into the waiting room. Because suppose that you've won all the way up to this moment, then this means that you definitely have this much money, right? So like this is the current amount of money you have. So if you lose, then this is the amount you would lose. So and then this loss, I will just write it as I minus 1 over 100 times 2 minus 1 over 2 to the I minus 1. So we should continue gambling while the wins are greater than the loss. So just while this is greater than this. 2 to the I minus 1.
I have a question.
Yes.
So what we are trying to find here, so we're simply trying to find the odds of winning, and by the way, is the one in between 1 divided by 2 to the I, is that a multiplication sign?
Yes, that's a dot.
Oh, okay.
Yes.
Yes. So the one, this over here, it shows the probability, the net probability of winning. And if it's
Oh, wait.
greater than the net probability of losing, we should continue gambling. That's
Oh,
what
wait,
you
no, like, let me make something clear. We're not calculating net probability. The net probability is given in the problem. It's already given. What we're calculating is an expected value. So in case you're unfamiliar with this, the expected value of some variable x is
Yes.
Andrew. Okay. It's a sum of the probabilities in each case, like every single probability multiplied by the value of x in that case, pi times xi.
Yes.
Yeah, so you know this. So also whoever is like selecting all of this, like please stop selecting it, otherwise it makes it like hard to see. Okay, thank you. So but either way, so this is the expected value of the amount you win. This is the expected value of the amount you lose. This is expected loss. So while your expected gains are greater than your expected loss, of course, it is rational to keep on going. Then our equation just simplifies into solving this one. So once you move everything onto one side, so eventually after simplification,
Alex, sorry, I have to pause for a while. Can you let everyone follow you? Because right now the screen is not moving.
oh, what happened? Oh yeah, I think someone followed like selected share earlier. Okay, here.
Mhm.
Can everyone please follow my view? Okay. So when we simplify the expression, it becomes 99 plus I greater than or equal to I minus 1 times 2 to the I plus 1. And at this point, it is simple calculation. In order for this to be satisfied, we must have I less than or equal to 4. So while I less than or equals to 4, keep gambling. In other words, you should gamble exactly 4 days. So, yes, Kevin, do you have a question?
Can we assume that that Bob has won every game before the ice game?
Yeah, exactly.
Like,
that
what
is
if he loses? Would you consider that?
if he loses, then the game has already ended. There wouldn't be any game after that, so there's nothing to consider, right?
So you can't gamble after losing.
Yeah, if you lost, then you're
Okay.
already dead in a sense. I believe. So what the problem says is that if he loses all the credits accumulated so far, and he has no more money to gamble. In other words, he can't do any more gambling. Yeah. Stefan?
So could we like see our responses? Because like I forgot my response.
You forgot your response. That's
Yeah.
okay. We can like try to get send back all the responses after this is over.
Okay.
Okay. So does anyone have any questions about why it's 4 days?
Yes.
Jay? Okay.
Yeah, so the expected value is of f of x is sigma from pi. So pi,
It's
but
the
like what is the top one? Like what is the top of the sigma letter?
I don't quite follow. Oh, like as in, so if you just think about it, expected value, you have a bunch of events. Each
Yes.
event has an assigned probability and an assigned value. So
Yes.
expected value is the sum of the probability of each event times the value in each event.
Yes.
Yes. So that's what it means. Yeah. Okay. So no one had any questions? Okay. Then let's move on to the second question. Yeah, so this is an interesting number theory problem. How many people solved it?
Can you say the answer first? So we know we actually solved it.
Oh, sure. So the answer to this question is 2 times 3 to the 198. It's 2 times 3 to 198. So in other words, the answer is 2 plus 3 plus 198 equals to 203. Anyone who got this right? No one? So like none of you got this one right at all? Are you sure?
I got 2 times 3 to the 99.
Okay, that sounds close. I feel like you made a small error somewhere. Wait, did you directly do totient of 3 to the 100? I think maybe you like did the first step, but not the second one. But sure, like you could you like quickly talk about how you did that? Like maybe your ideas because you
so
may be
like
only
the-
like halfway there.
In like 3 to the 200, there's like, it's like 3 to the 200 is 3 to the 100 squared.
Yes.
So like there's 3 to the 100 different squares. Plus 1 squared, 2 squared, all the way to 3 to the 100 squared.
Yes.
So I just took 2/3 of that.
Okay. So, but I think you need to like pay attention to these because a number A is n good if it can be written in this form. Emphasis on all must be co-prime to n, and B must also be co-prime to n. Because I believe the way in which you computed it, I think you like I'm not sure exactly what you did, but I think you really did not count all of them. Okay, so so let's go over the actual method. Okay. So first of all, let's just count all of the perfect square residues mod 3 to the 100. Okay. Oh, wait, okay, so first of all, let's count the set of a squared mod 300, 3 to the 100. Let's see, how many residues can this thing have? Oh, wait, yeah.
Alex, I think you need to explain to everyone what is the residue here and
Residues are just
yeah,
the
that you need to
I think it
introduce
just
this
means mod.
concept, right?
Yes. Residues just means mod. Like as in if I say the residue of 5, mod 3 is just 2. I think this should be self-explanatory. Yeah, but let's talk about how many residues there are. Oh yeah, and by the way, Asher, I just want to point out, there's a small issue in your earlier thing. When you said that the only remainders mod 3 to 200 are 1 squared, 2 squared, through 3 to the 100 squared, mod 3 to 200, actually these are not the only ones. I believe usually what you should be doing is like go up to 3 to the 200 minus 1 over 2 squared, not this one. Okay, well, that's something we can get into later. But either way, that was like a big undercount. Okay, so let's talk about how to properly do this. So how many perfect square residues are there? Does anyone know how to just do this mod 3 to the 100? No? Okay, so let's talk about this. Let's first list out everything. Of course, there will be a lot of repeats. 3 to 100 squared, or also known as 0 squared. So we want to find out when exactly there will be repeats, right? So like, because we only want to count the distinct ones. So when is there a repeat? So there is only a repeat when like we have x squared congruent to y squared mod 3 to the 100. Well, x and y are different remainders mod 3 to the 100. So does anyone have any suggestions on how to like turn this into something that's more doable? Because this still looks exactly like our original, right? Didn't really change. So the answer here is some difference of squares. X minus y times x plus y. This expression is equivalent to this. Hope everyone agrees. This should be fairly basic. Okay. And also note that because x and y, so over here, and also wait, let me quickly write another condition. A squared mod 300, how many residues are co-prime to 300? No, co-prime to 3. Okay. And also the extra condition here is that x and y are both co-prime to 3. X and y co-prime to 3. Okay. So given that x and y are co-prime to 3, so you know that you cannot have both x minus y and x plus y being a multiple of 3. Does anyone know why? Like just a quick question. Given that this should be something that you guys should know how to solve. That 3 does not divide x and 3 does not divide y. Prove that that this is impossible, that it is impossible to have three divide by x minus y and three divide x plus y. So this is just a mini problem. Can someone please solve this? This should be very basic, like one of you. Yeah, if you guys don't talk, I'm gonna have to cold call. Let's see. Advic G. Do you know how to just? Oh, Asher, sure.
What happens when x equals 1 and y equals 2?
When x equals 1 and y equals to 2, this part is true, but this part is not. I'm saying that it is impossible for both to be true. Right. Okay. No one, really? Okay, so let's do a proof by contradiction. So we all know what proof by contradiction is, right? Suppose 3 divides x minus y and 3 divides x plus y. Then what this means is that 3 divides 2x. Then what does this mean? Anyone?
X is congruent to 0 modulo 3.
Yes, 3 must divide x. But then this is a contradiction to our earlier thing that we said 3 does not divide x. So contradiction. Okay, let's go back to our original problem. We just showed that we cannot have both of these being multiples of 3. Then this means that only 3 to the 100 either divides x minus y or 3 to the 100 divides x plus y. So in other words, this means that either x congruent to y mod 3 to the 100 or x congruent to negative y mod 3 to the 100. Okay. So let's talk about what this means. Some of you might have already forgotten what the original problem was, or like what our original goal here was. Our goal is to find how many quadratic residues are co-prime to 3. How many distinct quadratic residues are co-prime to 3. And what we did is we first listed out all of them, but then of course there are bound to be repeats. And then we showed exactly which of them repeat. So if we know which of them repeat, then I mean, we can just list out the distinct ones, right? Because we said it only repeats when x congruent to y or x congruent to negative y. So then this means that among all of your 1 squared, 2 squared, 4 squared, 5 squared, all the way to 3 to them. And also this should be changed, 3 to 100 minus 1. To 3 to the 100 minus 1 over squared. Okay, so we know that exactly these two are repeats. These two are repeats, and basically we can pair these, right? These are the repeats. So okay, so then now let's find out exactly how many such quadratic residues there are. The number of quadratic residues.
For like a residue to appear more than 2 times.
A residue cannot appear more than 2 times, Kyle, because like we just showed, the only time that x squared congruent to y squared mod 3 to the 100, it can only be one of these two cases. Wait, do you understand? Like, if you have any more questions, like, please ask, because I don't want you to be confused about this one. Yeah, okay, so but it can only repeat in one of these two cases. So in other words, these are the only repeats. Why must we have x and y are co-prime to 3? Okay, so Robert, this is about the initial given condition, because I believe our given condition was to find the squares that are co-prime to 3 to the 100, right? Just in the condition that all is like if we go back to our initial problem, our question was if it can be written in the form all plus bn, where all and b are co-prime to n. Just this already means that this number was the co-prime to n, right? So we must have like a squared co-prime to 3 to 200, or just a squared co-prime to 3, or yeah. So but then what this means is so number of distinct co-prime residues co-prime or also square residues, that this is exactly quotient 3 to the 100s over 2. So about the totient, this just means the number of co-prime residues of 3 to the 100. But either way, this is exactly 2 times 3 to the 99. Okay, so this is only our first step. 2 times 3 to the 99 is the number of quadratic residues which are co-prime to 3 to the 100th. But then remember, what we wanted to do was mod 3 to the 200. Okay. Now suppose a squared is congruent to r mod 3 to the 100, first of all. Then we consider a plus, just consider all of these. Or just in other words, like all numbers that are congruent to a mod 3 to the 100. So basically, because we try to go one level up from 3 to 100 to 3 to the 200. And where k can practically range anywhere from 0 to 3 to the 100 minus 1. So then this would be congruent to, if we quickly do some calculation, this becomes r plus 2 ak times 3 to the 100th mod 3 to the 200. Everyone can keep up with this, right? This is just by expanding the square. Notice that the k squared times 3 to 200 cancels out because it's 0 mod 3 to 200. Okay, so in other words, we can achieve all remainders of this form. So for remainders of this form, in fact, like let's say we vary k over 0 to 3 to the 100 minus 1. And because 3 to the 200, 3 is like odd, or maybe how should I describe it? Perhaps I should describe it in simpler terms. If I instead talk about it like this, r plus 3 to the 100th times k, or actually 2a 3 to the 100th times k. Actually, I'll just put 2ak together. Never mind. I'll just put 2ak together. But either way, by varying
Alex, can you rewrite it? Because you scratched
okay,
too
okay,
much.
I know. By varying k over this, well, actually, I'll just keep in this form. By varying k over 0 to 3 to the 100th minus 1, we can make 2ak cover every single remainder, cover all remainders mod 3 to the 100th, right? Does anyone know why this is true? Okay, I can quickly explain this because like for any modulo C mod 3 to the 100th, because we have that A is co-prime, please stop sharing my guest here. Because we have that A is co-prime to 3, so thus this thing is invertible, so we can just simply set K congruent to C times 2A to the negative 1, mod 3 to the 100th. Okay, but either way, this is like one part here. Okay, so but basically, let's quickly review our claims. First of all, claim 1. We have 2 times 3 to the 99 square residues mod 300 mod 3 to the 100 that are co-prime to 3. And our second claim, if there exists some A such that A squared congruent to R mod 3 to the 100, then there also must exist, then for any K, there exists a B such that B squared is congruent to R plus K to the 100, K times 3 to the 100, mod 3 to the 200. Yeah, remember, these are two very crucial claims. Like, you guys should later, after class, review this, like, come back to see how we prove these two claims. But once we've already proved these two claims, then the problem overall becomes easier. Because remember our original problem, we want to find out all squares of the form R plus Bn, mod, that are congruent to this mod 3 to the 200, where R is co-prime to 3, GCD R3 is equal to 1. and GCD B3 equals to 1. Right. Okay. So then and since we've already like literally enumerated out all of them. Oh yeah, and by the way, this all is the condition is that this all must be co-prime to 3. GCD all 3 equals 1. Okay, so but either way, now since we've literally like almost like practically listed out every single possible remainder that's co-prime to 3 mod 3 to the 200. So we can just count how many are there such that for the B here it is co-prime. And the answer for this part is that since like B can literally like range over anything, like because of our earlier proof, we see that B can literally range anywhere from 0 to 3 to the 100. So then over here, the exactly 2 times, so again, we take a totient 3 to the 100 equals to 2 times 3 to 99. Like basically, in other words, for any fixed value value, we can then find these corresponding ones. There are 2 times 3 to 99 of these. So then our final answer is going to be 3 times 399 times 2 times 3 to 99 equals 2 times 3 to the 198. I should go back here. Yeah, wait, and also, wait, sorry. Okay, so either way, so this is our whole proof. So a quick recap. First of all, we find the number of residues mod 3 to the 100, 3 to 99. We prove that for every such residue, we can scale it up and like find the corresponding ones mod 3 to 200. And we show like that there are exactly 2 times 3 to 99 corresponding ones that satisfy the given constraints. So thus this is like the number of R. And this is the number of B for any corresponding R. Number of corresponding B. So our answer is 2 times 3 to the 198. Okay, so if anyone has any questions, like please ask because this is a difficult problem. And also we won't have time to go over this right now, but then this is like extra. This is something that you would want to like look at once you get home. There's something known as Hensel's lemma, which can greatly simplify this. Yep, so that's all. Okay, no questions, then let's move on.
Actually, I have a question.
Yes, go. Okay.
So, first of all, I have many questions, but first, do you know what a residue is?
I explained this at the beginning, but like just think about a residue as a remainder, mod some number.
Oh, okay.
Yeah. Okay.
Distinct. Okay.
If there are any more questions, like you can like private message me in the chat, but I think for now we must move on. So I think it'll be Kennan or Edward next.
Okay. So, I'm sorry, so, yeah. Um, wait, so, I'm gonna go over my problems. So, okay, so, why is this like moving? Okay, kill some, yeah, okay, okay, so let me copy over the question. So my first question was problem about characteristic equations. So here, no, not that. Oh, here we go. Okay, so this is the question. Did anyone perhaps solve this question? Raise your hand if you did. Huh, nobody solved this question? Also like did anybody like try some things out and find a pattern and then solve it? Or did no one solve it? Looks like no one solved it. So does anybody have any questions about this problem? First of all? Oh, everybody's so quiet.
I think I have a question.
Yeah, what's your question, Jay?
So by 4 times, is it 4 times a sub n minus 1?
You
Or like
mean
where
by
a sub n minus 1 are in parentheses?
uh where are you here?
Yes.
So it's 4a sub n minus 1 like that.
Oh, okay.
So yeah, n minus 1 in parentheses. Does anybody else have a question? Or did anyone else did anyone like solve it? It's not an easy question, so okay, I guess no one solved it, which is
Wait, are you supposed to use the characteristic equation here? To like
yes,
uh,
you are. So did anybody solve this equation even if you didn't use like the characteristic equations? Okay, looks like nobody did.
Alex 啊，你就帮 Edward 只看这道题就行了哈。哦，sorry。
Okay, so maybe don't put random stuff on here. It's quite so for this question, we can start with the series a(n) equals 4a(n) minus 1 minus 4a(n) minus 2 plus 1. And so this is what's called a recurrent solution, and we're trying to extrapolate it backwards into the negative direction. And so how's that gonna work? Well, uh, we're going to find the general formula, which automatically applies to basically all the numbers. So in order to find the general formula for this, we're basically solving for a(n), right? So a(n), this linear, this recurrence relationship has, we can use a couple words to describe it. So the first word is linear. So you see, there's no square over here, so it's just a normal a(n) minus 1, so it's linear. That's the first important thing we need to notice. The second important thing we need to notice is that it's second order. If this or in other words, we have two of these terms, and it extends back to n minus 2. So that also makes a big difference. And the last difference is the last key fact is it's in homogeneous. This is probably what makes this problem harder, is that we have this plus 1 at the end, and it's sort of annoying. If this will work. God. And so what we do in this case, in order to solve this linear second order and inhomogeneous recurrence relationship, we can first ignore the plus 1. So let's define Bn to be this Bn minus 1 minus 4Bn, as this is our recurrence relationship, and by a theorem, you can see that an equals Bn plus a specific solution. So what we're doing right here is we're sort of like ignoring that we have like these initial values here, and we're just trying to find the general solution based on the recurrence part. So obviously this general solution is going to have multiple like unknown variables. But so first of all, we need to find this special solution here. So just any solution that satisfies an. It can have any initial values. So does anyone want to like give an example of a very simple solution to an that can like fill in this blank here? Okay, so I guess that's no.
I want to participate.
So yes, Jay?
Yes. So in this case, I think this could be 1
So an equals 1?
No, that an is bn plus 1.
Yes, so an equals 1 is our solution that we can put in here.
Yes.
Okay, so that is correct. We can like show this is true by considering an equals 1 as our solution. So what we do here is we substitute 1 in. So we do see that 1 equals 4 times 1 minus 4 times 1 plus 1. So this works, and we can put 1 in this blank here. So that's very good. It's just a general solution. You might notice there's it doesn't really apply to the conditions given in the problem, but that's okay. We just needed one solution. So now we established that an equals bn plus 1. So in order to solve bn, which is a linear second order and homogeneous recurrence relationship, we use something called characteristic equations. And what we're really trying to do here is that we need to find now two solutions of Bn. And so for these two solutions, the general fact is they always come in a form of a to the n. For these type of relations. And so what we're going to do here is we're gonna assume the to the power of n is a solution, and we're sort of solving for this a. So we're gonna do a to the power of n equals, actually I shouldn't be using a, but it's okay. 4a to the n minus 1 minus 4a to the n minus 2. There should be a minus 2 here. And so we need to solve this equation to find our a in the solution a to the power of n. Does anyone want to solve this equation?
Yes, I want to solve it.
Yes, Jay?
So I think a is equal to log of the logarithm of 4 a to the power of -1 minus 4 times a to the power of n minus 2 to the base n.
So that is potentially correct, but it's not very clear what you're saying. So I'm gonna give you a hint for the first step. That we know we don't actually want a to equal 0, so we can cancel out most of the things to get this a squared equals 4a minus 4. And so now do you know the simplified version of the solution?
Wait, but how do we know that? Oh, yes, we know that a squared. Yes. Yes, now I understand. So
Okay.
a is equal to wait, a because a squared is equal to 2a is equal no. A plus b squared is equal. I'm not sure. Should we use the quadratic formula?
This can be factored.
Oh, yes, it can be factored. Yes. Thank you really much. Yes. I will use the quadratic formula for this. Yes, so what I would do is I would say that a, although your solution is probably better, x here would be equal. So we're trying to solve for a.
Yeah.
A would be equal to -4 plus or minus the square root of 4 squared minus 4 times this times -1 times 4. Yes, and divided by a2.
Okay, so that is correct. And if you simplify this, you get 2. So what happens here is that our solution is 2. And so we know that 2 to the n works as a solution to b to the bn. But there arises a problem here. Usually there's two roots to the characteristic equation, and so we can find the two desired solutions. But there's a issue here that we have a double root and we can't really put the same solution twice. So now we have to sort of not obey this rule of a to the n and sort of find another general rule, a general solution. So it's not exactly easy to come up with this solution on the spot. So it's usually you usually should know that the solution is a to the n to the power of a n, where this a is the same as the one we found. So our two solutions would be 2 to the n and n times 2 to the n. So now that we have these two solutions, we can solve for the general solution of Bn. So given any initial values, we can find that Bn is equal to some constant lambda 1 times 2n plus some constant lambda 2 times n times 2 to the n. So basically, like sort of like a sum that has like multipliers in the front. So we basically have this as our general solution. So now we need to go back since our initial condition is based on A. If you can see here, so it's A, right? This doesn't say B1. So what we're going to do is we're going to convert this back into the equation about A. So we get AN equals, remember how we had this equation here. Now we're going to use this equation and find that an equals lambda 1 times 2 to the n plus lambda 2 times n times 2 to the n plus 1. And so in this case, we have our two conditions that a1 equals 1 and a2 equals 2. And so what we can do here is we can list a set of linear relations to solve for this. So we have lambda 1 times 2 to the 1 plus lambda 2 times 1 times 2 to the 1 plus 1 equals 1. And our second one is lambda 1 times 2 to the 2 plus lambda 2 times 2 times 2 to the 2 plus 1 equals 2. So this is our n equals 1 case and n equals 2 case. And so what you can do here is that you can solve it. It simplifies. It's not very hard to simplify nicely. So I won't go over that, but the final solution is that lambda 1 equals negative 1 over 4 and lambda 2 equals 1 over 4. And that makes our equation negative 1 over 4 2 to the n plus 1 over 4 n times 2 to the n plus 1. So this is our an. And so we can simplify this a bit since we see a lot of common things. So we can get that this equals 2 to the n minus 2 times n minus 1 plus 1. And so what we can do here is that we have found a general formula for an based on our initial conditions. So now we can bring it back to the problem. And so we encounter this a over 2 to the power of b expression, and we are trying to find for the negative ones the value of b that differ by at least 9. So in this case, we're looking at our a over 2 to the power of b, right? So we have a over 2 to the power of b, and in this case, this is equal to n minus 1 over 2 to the 2 minus n, and remember n is negative, so this expression will turn, the exponent will be positive instead. Plus 1 equals n minus 1 plus 2 to the 2 minus n over 2 to the 2 minus n. And so in this case, you're trying to find b. So what is this equal to? Well, it's one possibility that it is just 2 minus n. However, this is not quite the answer, since if n minus 1 is odd, is even, then the value would be less than 2 minus n. And so this is where it rises the possibility that it changes by a large number. So what we do here is we use a notation called like a v. So v base 2 of v sub 2 is basically the highest power of 2 and a number. So v sub 2 of 16 would be 4. V sub 2 of 48 would also be 4. And by definition, v sub 2 of like an odd number such as 5 equals 0. So given this, we can sort of see and write in a mathematical notation what we're doing. So b would equal to 2 minus n minus v sub 2 of n minus 1 plus 2 to the 2 minus n. And so in order to simplify this, we can see that 2 to the 2 minus n would never really it would like always be a higher power of 2, and so it doesn't really matter. So for example, if n minus 1 was divisible by say 2 to the x, then it's sort of, you can tell that 2 to the 2 minus n would also be divisible by 2 to the x, since n minus 1 is much the power 2 minus n has to be much greater than x. You can sort of think of it that way. So in this scenario, we can just like ignore this second part. And so this is b was here, right? So b is equal to 2 minus n minus v2 of n minus n minus 1, I think. So n minus 1. So in this case, we sort of get this expression. So we can see that this part changes. If we look back at the problem, we're considering we're considering n and n plus 1. So what we do here is we consider n and n plus 1. N plus 1 as like sort of like a change. So this first term can change by up to 1 in either direction. If you look at the second term, for values like 2040, negative 2047 to negative 2000, actually this is backwards. For expressions such as negative 2048 to negative 2047, we can see that this changes by 12, which is lots. So this can literally change by anything in any direction. So it's sort of our like change this like sort of thing. So we need to change by a total of at least 9. And so this can only change by 1. So we need this to change by 8. When can this happen? Well, it can happen in numbers such as 256 to wait. It can happen in numbers like negative 256 turns into negative 255, negative 257 turns into negative 256, negative 512 turns into negative 511, and so on. And so what we do here is we can consider each case individually. And we can plug this in back into this to see how much it actually changes. For example, this first one, we can plug it in, and we can see that negative 256 for this, the b is equal to 258 minus 258 minus 8, and for the second and for negative 255 we have b equals to 257 minus 0, and this is 250 and this is 257. So oh wait, sorry, this is v of n minus v2 of n minus 1. So anyways, in the end, you can sort of see that this one I think works. You can check. So 258 minus v2 of 257, so n minus 1, negative 257, and the second one is equal to 257 minus v2 of 256, negative 256. So this one is equal to 258, and this one is equal to this one is equal to 249. Yeah, 249. Wait. 240, yeah, 249. And you can see that these do differ by 9. So this one works. But you can next try this one, and this one doesn't work. So it tells you to find the it says here in the problem, find the absolute values for the greatest 3 n's. And so we can list this on, and so negative 513 to negative 512. This one works, and this one doesn't work. So we have to continue. We have negative 768 to negative 767, and negative 769 to negative 768. This one works. So now we're done. 1, 2, and 3. And we can add it up to get 1,536. So that is our answer for the first question. Is there any questions?
Yes, I have a question.
Yes, Jay?
So, it starts a few lines up where we say that, where we know that, using lambda 1 times. Yes, so my question is, how do we know? So if we know that lambda 1 times 2 to the 1, let me actually draw an arrow. If we know this here,
This one?
how do we figure out, 1 second, how do we figure this out?
This one?
Yes, how do we get from here to here?
So how does this step work?
Yes, first let's do to this step. So we get that lambda 1, sorry, 2 times lambda 1 plus 3 times lambda 2 is equal to 0, right?
So we have 2 times lambda 1 plus 2 times lambda 2.
Oh, so the 1 is in the parentheses.
It's multiplication. So lambda 2 times 1 times 2 to the 1. Yeah, this isn't a parentheses, this is a 1. If
Mhm.
that's what's tricking you. So this is a 1.
Yes, so to solve it, we simply say that, so is lambda 1 equal to lambda 2?
No, they're different. You can see here that lambda 1 is one
Oh,
fourth and negative 1/4 and lambda 2 is 1/4.
yes. And to solve these two equations, we subtract from the two sets of equations.
You can do that. It's not the only way to do that, but if it's the way you feel the best about, yes, you can do it that way. There's like multiple ways you can solve these equations.
Yes,
Yes.
and also, will we get the solutions after we're done with the class? Because I want to look over them.
I think so.
Oh,
That's
okay.
not really a
Thank you.
question for me, but
Thank you.
Yeah, we will share the recordings and the solutions and also the problem sheet after each session. Yeah. So no worry about that.
Okay, good.
okay, so is that the last question for this question?
I think so. Well, yes, I think so.
Raise your hand if anybody has a question, please.
Can I solve this one?
Yes, you can solve this one.
Okay, so I believe maybe this is because I'm wrong. I think this is relatively more simple than the other problems.
Yes, this
So
is more simple than my first problem.
so we see that the GCD of A, B, and C. So A, B, and C are co-prime. That's what we know. So we're trying to take out the largest amount of co-prime numbers from the set between 1 and 100.
Let me stop you here for a second. You might not be wrong, but I just want to mention that the fact that GCD of A, B, and C equals 1 does not mean that A and B are co-prime.
Wait, is the answer to this question 30?
Yes, the answer is 30.
Okay.
So it is not true that A and B are co-prime. It's true that if a number D divides both A and divides B, it cannot divide C. But it's not true that A and B cannot share factors. So does that change your solution?
I got 15 as my solution.
Oh, then that I don't think that is right.
Yes. Yes.
No, okay, I can share my solution if you want.
Okay, can you share your solution?
Oh, okay. Wait, should I like focus or?
Yes, can you click the follow my view or whatever button it's called? Okay.
Oh, okay, this works. So from GCD, from this condition, we know that each prime factor, or yeah, prime factor, it can only be shared by at most two numbers in the list. Because if there are three or more numbers that have this prime factor, then this won't work anymore. So what I would do is I would list out, say, the first few numbers and see if there's any patterns. Say 5, 6. So since we want the first or two numbers of any prime, so for example, we have 2, 4, 6, 8, dot, dot, dot. We want to choose two out of the 50 numbers. And then for like factors of 3 or products of 3, we also want to choose two of them. So the trick here is that if you say pick a number 6, 6 belongs in two groups. So it's actually a bad choice because it spans two of them. And so rather you'd want to choose 2 and 3 because they only take one of their group. So you can
So
choose
let
another
me
number like, yeah.
okay, so let me stop you here for a moment. So when I first approached this problem, this is also what I thought. Um, and it's the first few steps are very good. It's not wrong that it's choosing sex is not good. Um, but it's not exactly like the most well, like it doesn't apply to like everything. So it's correct that you shouldn't choose 6, but it's not like you shouldn't like expand it to like every single number. Does that make sense? But like otherwise it's correct.
Yeah, it's supposed.
Yeah.
So what I did was I just chose every single prime number between 1 and 100 first. So if you write them all out, you'd get 25 prime numbers in total. However, this is not the entire answer because for each prime factor, we actually can use 2 numbers. What I did here was I just chose the square and saw how many squares I could write. I chose squares because literally any other, like, what do you call it? Product of 2, like 2n, won't work because n, if say n is divided by 3, then you'd be spanning 2 groups, and so that wouldn't be the most optimal choice. Can you understand that?
Uh, yes. This is what I talked about with 6. Um, you can assume that it's true, but we can see that it's not necessarily the best
Like
choice.
if you choose 6 here, right?
Yeah.
You'd only get 1 number because you
You
can't
wouldn't, yeah,
choose
you wouldn't choose,
any
you,
other 2
you
numbers.
probably wouldn't want to choose 6.
As opposed to if you choose like 4 and 9, then you get
Yes.
4 numbers here.
Yeah.
Yeah.
So yes, in
So
this case,
anyway, you'd see that you have, is it 81?
um,
925. But yeah, this does not exist. And there's also
you're,
one. So basically, when we write it out, we find that there are 4 squares that work here. So we can add 4 to this solution. And then finally, we also have the 1 because the GCD of any 2 numbers and 1 is always 1. So if we add them up, we get our final answer, which is 30. And this happens to be our most optimal setup.
this is almost exactly how I thought of it when I first did it. Um, so it's a very good solution, and if you're working on this and use this solution during a contest, it's perfectly okay. It reaches the right answer, and most of it is correct. But I will present my solution, which has some slight differences. Um, so first, wait, let me do this. So what I want to do first, why are people moving things around? Okay, so anyways, so what I start off in the same way pretty much. So I see that each prime number can only be used twice. And so in this case, which prime numbers can only be used once? Well, those are the prime numbers from 50 to 100. And in that case, there are 10 elements.
I have a question.
Yes, Bowie?
Are these questions from like AMC 10 or like what competition are they from?
No, we came up with these questions, so I don't think they'd be anywhere if you search them up.
Our problem, the difficulty level ranging from AMC 10 to easy Amy problem. Yeah, so the problem so far, the 4 problem you guys we have, talked about probably a little bit, hard, on the hard end of the AMC 12 or, or the intermediate Amy level. Okay.
Yeah. So there's 10 elements from 50 to 100. What?
I cannot see the board, sorry.
Yeah, it's not just you, by the way. Did anyone close the board?
This is interesting. Let me see. What is the whiteboard here? Yeah.
What happened to the white?
I don't know. I think it just accidentally closed or something. Not sure.
Why don't then I make a new whiteboard? Oh, maybe it's this one.
Oh, that's weird. It refuses to load now. I think it's like some issue with the Zoom.
Uh, yeah, reload, reload, reload.
Oh, I know because I set up this meeting for 2 hours. Yeah, let's turn off and then.
Okay, I close. Okay, you can
Wait,
share
wait.
the new one.
Can you share the meeting? Can you share the whiteboard again? Let's rejoin the meeting. Wait a second. Let's find out.
It shows
Where
it
is
still
it?
has like 9 minutes left, so the whiteboard shouldn't have closed.
Yeah, because I assume this meeting can be end like in 2 hours, but turned out we spend more time
It
on
might
it.
be because the whiteboard crashed or something. Like maybe creating a new whiteboard would fix this.
But the meeting gonna end in 2 hours. In 9 minutes.
It doesn't end.
No, it won't end because you have the paid version. Only the unpaid version forcefully closes.
Yeah.
But when I set up this meeting, I only set up for 2 hours.
That doesn't matter.
It doesn't matter.
Oh, really?
It doesn't
Oh,
matter.
okay.
Okay, so I'm gonna copy this over, and to prevent like the crashing of the whiteboard, like what happened, I think, I would recommend nobody
Alex,
except
can you start a recording? Oh, okay.
it's still recording. I would recommend that nobody like draw random stuff because it might be that we drew too many things, and the answer is 30. So maybe that's the issue. I don't know. I'm not sure, but just avoid drawing random things because it's also distracting. And we want everyone to focus on here. Okay, so let me continue my solution, uh, and try not to lose more time. So our step after including to summarize, we had the 10 numbers from 51 to 100, which are primes, and we had the number 1, so 11 in total. And so what's gonna happen next is that we're going to and more numbers. So we can basically add all the primes from 10. We can add more numbers from 10 to 50. But I'll first explain why we can do this. So we will consider there are 3 types of numbers. Primes, powers of primes, and composite numbers. That aren't powers of primes. So for composite numbers, we have that they have to have the factor of 2, 3, 5, and 7 somewhere in them. So what this means is that 2, 3, 5, and 7 are what we can really not waste. So this is why 6 doesn't work, since it uses like 2 of these at the same time. But 4 is okay since it only uses 2. So given this, we can include numbers such as 2 times 11, but not like 2 times 7. So this is a main point of the question. And so given this, we're not focused on the primes from 10 to 50, so we can include all of these ones, which I think gives us 11 more, so 22 in total now. And you see that we can use each of these twice, right? So in total we have 2 times 4, which is 8 possibilities. And we can see that 22 plus 8 is 30. So 30 is our answer. But we should always try to we should also try to construct can okay, so we also have to construct our values to make sure it's possible. So in this case, we can set our 2 uses of 2 to be 2 and 4. I think like the previous solution, or we can set it as 14 and like 26, for example. Or we can set it as 2 and 26, or 4 and 26, and so on. There's a lot of possibilities here, but that's something you can do for 2, and you can note that doesn't always have to be like primes or prime powers. We can also have composite numbers. So yeah, that's my solution for this problem. Is there any questions?
Yes, there. So I have a question. So
Oh,
I
yes.
do get how you got 22. It's because I think you found the number of prime numbers from 51 to 100, and then 1, and the square. I think it is because the square of each number and the number itself would not have any factors with two of the numbers. Is that correct?
So to answer your question, 22 is 1 plus the number of primes from 10 to 100. And so that's where we got 22 from. So those are what we guaranteed to have in our set. And so for the 8, if that's what you're asking about,
Yes.
so we can sort of only use 2 twice, right? We can only have 2 in 2 numbers. Does that make sense?
Wait, but how do we get 8 from that? Yes, I do understand how we can use 2 for only 2 numbers, because then after adding a third one, then it would become the GCD of these 3 numbers would be greater than 1. But how does
Yes.
that contribute to adding an 8?
So, notice that this is also true for 3, 5, and 7, right? So in total, we can use 2, 3, 5, and 7
Yes.
2 times each.
Yes.
And that's 4 numbers. So we sort of have 8 uses in total.
Mm-hmm.
Does that make sense?
Oh, so because we can use out of these 4, 2, 3, 5, 7, we can multiply and we can multiply them twice. I mean, we can make 2 of these, such as 4 would only have in common 2. 6, actually 6 wouldn't work.
Yes, 6
Actually
would
9,
work.
yes, 9 would work. 25 would
9
work,
would work.
yes. 49 would work. So how would wait, why is it only limited to 2, 3, 5, and 7?
Because 2, 3, 5, and 7 are the ones we must have in composite numbers. And they're also the only ones we can have in squares. So if we have a composite number, we're guaranteed to have 2, 3, 5, and 7. And if we, yeah, so like, that's why we sort of have to like,
So I understand why it can only be working in the square, because anything that would be squared, like 11 squared, would be greater than 100. But what do you mean by any composite number is made out of 2, 3, 5, and 7?
so for every composite number, say we take a composite number 86. So that's
Yes.
2 times 43. So you see we have a 2 here.
Yes.
So
So
for
any
every,
yes. So any composite number must be made out of 2, 3, 5, and 7.
they must contain 2, 3, 5, and 7. They don't have to be exclusively 2, 3, 5, and 7, but
Yes.
they have to have 2, 3, 5, and 7, which is like sort of the limiting factor.
So they have to have one of 2, 3, 5, or 7.
Yes.
But
Does
what
that make
about
sense?
the number 143?
143?
Oh,
Well,
that's
that's more
greater
than
than
100.
100. That's greater than
Yeah.
100. Okay, thank you really much. Now I understand your solution.
Does that make sense now? Okay.
Yes, yes.
Is there anyone, any more questions? Okay, I think that's it. So, I'll let the next person present their solutions to their problems.
Right. Right. Uh, okay. So we have my first question. We'll paste it. It doesn't matter. But anyways, this is our question. Suppose for a positive number. Next we have quadrilateral. Let me remove this.
Okay, with sides x2, 4 minus x2 in that order. Like, I guess count clockwise, whatever. And then it contains a inscribed circle of radius x. And then inside that circle, there's another inscribed quadrilateral in it that has corresponding parallel edges. So I'll draw a diagram first. So let me draw a totally random quadrilateral. Stop, guys, stop. Actually, stop post expand. So anyways, let's see. Okay. So here we go. A random quadrilateral. So okay, so and then we also have it. We label its sides. So actually, 2 of its sides are equal. So that doesn't really matter. 2 opposite sides. 2x 4 minus x. And it contains an inscribed circle. We know it contains an inscribed circle because, like, this theorem kind of you can look up later. But anyways, it just contains an inscribed circle. Okay. Okay. It's close enough to being inscribed. And then it has radius x with another inscribed quadrilateral on it. Okay, actually. Oh my. So then we have this. Wait. Okay, that has parallel edges. Like, what I mean is, like, this is parallel with the corresponding side. And then these 3. And then, okay, you get the idea. So then we know, and then oh yeah, and this has radius x. So we want to find x. So, like, first of all, like, how have we solved it? I'm just wondering. Anyone's, oh, well, this was a pretty easy question. So anyways, okay. So, anyone want to explain?
Sure, I can explain.
Oh yeah, sure.
Okay. Can I redraw the diagram?
Yeah.
Okay. So from the given sides, we have x2, 4 minus x, and 2. We also know that there's a similar quadrilateral inside this inscribed circle. We know that there are 2 sides that are equal, and since it can be inscribed in a circle, that means it's probably a isosceles trapezoid. I forgot where that theorem comes from, but it's there. So we know that this shape is an isosceles trapezoid. We can draw a line down the center.
Could you explain
Oh.
how you got the isosceles trapezoid? Just be clear.
Okay, basically,
Yes, it is correct, but, like, how do you know?
it says with another inscribed quadrilateral in it that has corresponding parallel edges. I'm assuming
Yeah.
that means that quadrilateral is similar. We know that
It's not similar, but, like, it's not like, for example, like, I have this rectangle here, and then I have, like, this square, like, it has parallel edges, but it's not similar. But you could do an angle chasing and get the corresponding angles are the same, so yes, it is still cyclic. The outside, okay, but you can go on.
okay. Anyways, we can draw the 4 lines that are normal to the 4 sides. We know that each of them are of length x. We can also draw these 2 auxiliary lines. Okay, so now, yeah, thanks. We know that this triangle, wait. We know that this triangle here and this triangle are congruent. We know that because they have a pair of same sides, and they have a shared hypotenuse, and they're both right angle triangles. So we know that this angle is equal to this angle. Similarly, we know that these two bottom triangles are also similar, because they also have same pair of sides. So we have these two angles that are similar. We can call this angle 1 or angle A, angle A, angle B, angle B. We know that these four angles added together give us 180 degrees. So A plus B is equal to 90 degrees. So A and B are complementary. So for this triangle, we have this angle is equal to B. And for this triangle, we have this angle is equal to A, because again, A and B are complementary. Oops. So now we have these two triangles. We notice that they're similar because they have all three angles are the same. Because we drew these as midpoints, we know that this side is equal to x over 2. No, that's not good, 2. 2, and this is 4 minus x over 2. So we can write their proportion sides as an equality. We know that x over 2 divided by x is equal to x divided by 4 minus x over 2. Solving, we get 4x squared is equal to 8 minus x squared. Wait, 4 minus x squared. And so x squared, wait, x squared is equal to,
Yeah, just saying this is 1/2. So you don't need to like,
no, I just multiplied 2 on both sides. 4 squared, squared. Okay, so you have 5x squared is equal to 4. And then you have x squared, or x is equal to square root of 4 over 5. And then you could simplify that to 2 root 5 over 5. Yeah.
Yes. So I have a question about this problem.
yeah.
I like your solution a lot, but I don't understand how you get from the diagram to x divided by 2 divided by x is x divided by 4 minus x divided by 2.
Oh yeah,
Yeah.
that's
This because
I understand the diagram though.
they're
That's-
similar triangles.
yeah.
Because they're similar triangles, they have similar proportions. So,
Yes.
for example, we know that this ratio to this is equal to this ratio to this, because again, they are similar triangles.
Yes, we know that x divided. Oh, 1 second. So the lower divided. That makes sense. Okay, thank you really much for your solution.
Wait. Oh yeah, just saying, Kevin, are you wait? Wait. Yeah, like Kevin, how did it wait? Also, I don't know if the wait. So what answer did you put in the answer sheet, Kevin?
Oh wait, no, I think I did something wrong here. Wait.
Yeah, because
No, the
I
answer is
think
equal to
X.
4 over 5.
Yeah, it's like
Yeah, I
hold on,
just
let's
did
see.
these stuff from.
Like, yeah, it asked us to find x. So, like, yeah, that's 4/5. But anyways, yeah, you got the right idea. But yeah,
Yeah, the answer is 4/5,
yeah.
but
Yeah. So also this was my way, so like it's kind of similar to yours, not exactly. So like looking at our original diagram, we have this, like as we said before, like what we did, like these two angles equal, these two angles equal, these angles equal, and so on. So like, if this interior, hold on, wait a minute. Okay, follow my view. Okay, so if this interior quadrilateral is cyclic, as we said, then the outside one is cyclic because this angle plus like this angle equals 180. So now, basically like the same thing. Like this quadrilateral is cyclic and has two equal sides on the opposite sides that are both length 2. So yes, it's an isosceles trapezoid. Then what I did is like so note that like the height of this trapezoid, isosceles trapezoid, is actually the diameter of the inscribed circle because like, yeah, like this is x. It's just kind of self-explanatory why this altitude is 2x. And then we have x, 4 minus x, right? So then like this thing down here would mean this is like 2 minus x, I think. And then like, yeah, you could just do the calculation. So anyways, this gives us like, let's see, what does this give us? Oh, so computing like this is 4x squared equals something. 4x squared minus 4x minus x squared. So that means 5x squared equals 4x. And then yes, again, like because because of Pythagorean theorem. So like basically we get x equals 4/5. And yeah, we got the same thing. So yeah. Okay. Does anyone have any questions about this problem? Okay. Very exciting. Okay. Great. Then I guess we're moving on to the next problem. So, okay. Sorry for the latex compiling. But anyways, okay, so here's our problem now. Bob is walking in the cells of this 10 by 10 grid. So anyways, like, I won't draw out the full grid, but like, you kind of know what it looks like. Like this. Oh no. Okay. So here's our like kind of like grid, and then we have a bunch like.
Can I try to solve this problem?
Oh yeah. Did you solve this problem?
I will try it. So I'm going to draw a cell. Oh, sorry about that. My mouse
okay.
went on the wrong direction. Okay, let's say this is a cell. I can't draw a 10 by 10 cell, but I will draw a 3 by 3 just to show an idea. So this
like Jay, can you click on
this
full
isn't
on
me.
view?
This isn't actually me. I am not the one who is making these. I'm just making this box. I'm not the one who did these blue ones, but here. Alice is in the bottom left corner and Bob is on the top right corner. So what we know is that Bob, so I found out a pattern. I'm going to tell you why. These points are the points where Bob and Alice can collide, the diagonal along this axis. So along this diagonal, the points along this diagonal.
Yeah.
First of actually, may somebody stop clicking on my square? Thank you. So how did I figure out that these points are where Bob and Alice can collide? So you see, Bob and Alice can definitely not collide on their first turn. Bob will go either left or out, or so they're going to be the square root of 2, I think. Actually, not necessarily, but they're going to be closer to each other. And then
Yeah.
let's say Alice goes here, then Bob can go here, Alice can go up, Bob can go here, and they will meet on this intersection, and so on. This one will go here, this one will go here, it will go down. And you see, once Bob goes to here, Alice has to be going up, but this one will take more, it will take 3 steps, which is impossible. Alice will not be
If
able to be
someone is
there.
not playing on the screen, okay?
Yes, may you please stop playing on the
Yeah,
screen?
is that Kyle? Kyle, is that you?
No. Yeah.
Yes. So the
Oh, I
proof
asked
here
them
is
if
that
the
B
format
cannot
was
reach
latex.
any of the points that are not along the diagonal by the time before A passes
I
them,
asked was if the
meaning that
format
there are
was
only
latex.
4 points. So how does this apply to a 10 by 10 grid? You see, on a 10 by 10 grid, there will be 11 of them, as it will be the dimensions of one of the sides of the dimensions plus 1. So we will have 11 of these points that can be contacted. Now, how do we figure out the probability? So we figure out the total, I think, once again, I likely got this problem incorrectly. We find the amount of points that would lead, that A would be going in the end. So it would be 10 ups and 10, let's talk about Atlas. It will be 10 ups, 10 rights. So it will be 20 choose 10. 20 choose 10 is the amount of ways it can go from one corner to another, Alice. If you're familiar, I'm pretty sure most are familiar with combinatorics if they're attending this class. So it'll be 20 factorial divided by 10 factorial times 10, sorry, 10 factorial times 10 factorial. Oh, sorry about that.
Can you follow your view, Jay?
Oh, wait, I can move my screen?
No, like click the follow.
Follow. How do I click follow? That's what I'm not sure. I'm not sure how to click follow.
We need to hurry up a little bit. It's already
Yeah.
9:17.
Okay. So it would
Yes.
be we know that will be 11 all the way up to 20 because 10 factorial would be able to remove it for 10 up to 1. So, and how do we remove 10 factorial from 11 times 12, so on and so on? So I think so 20 times 9 times 8 times, so 10 factorial is 40,320. And
Oh yeah, just say wait. I think you meant 19 choose. 18 choose 9.
oh, sorry about that. 18 choose 9. Yes.
Yeah. So
18 choose 9. It's 18 choose 9. Okay. So 18 choose 9 will be 18 factorial. It will just be the same thing. 18 factorial divided by 9 factorial times 9 factorial. This would lead to 10 times 11 all the way up to 18. And that will be divided by 9 factorial. So the 9 can be removed. 9 times 8 times 7 times 6 times 5. So 9, the top 9 here, can be removed, can be canceled out with the 18. And it will become 2. In addition, and that can actually also cancel out 9 and 2 would in fact cancel out. I think my ink is too light. 9 and 2 would cancel out with 18. With 16, 4 would cancel out. 2 and 2 would cancel out. And we're still left with 2. With 15, 3, 5, and 3 would cancel out. And 1 is actually not included. And with 14, 7 well, 1 second. 7 will be canceled out. And there will be an additional 2. Sorry, I cannot see my own ink. But yes, we're going to figure out what 20 choose 10 is. I did not figure it out yet. And what we're going to do is, I think we're supposed to do 20 choose 10. My final solution will be 20 choose 10 divided by 11. Although I'm not sure. I'm sorry, 18 choose 9.
Yeah, wait, also yeah, 11.
Kennan,
On.
I think we have limited time. So
Yeah,
I think
yeah.
you can, so Jay,
Yeah.
yeah. So I think let Kennan take over from here, like, talking about the whole solution, okay?
Yes,
Yeah.
yes.
Okay.
Sorry about that.
Just saying this is 2 to the 18 because Alice and Bob, they can they have to walk 9 steps before they meet. So like 2 to the 9 for Alice and 2 to the 9 for Bob. So that's 2 to the 18. So anyways, yeah.
Oh, okay. Yes.
Yeah. So,
So we
so
figured
if you,
out. Yeah. So we.
Yeah.
Yes, you're correct. You're correct.
So if we really want to calculate this, like, I don't even know. One of the, I think, like Alex posted this, but this is 12155 over 2 to the 16, okay? And it asked for this, so like 16, like 18 choose 9 over 2 to the 18. Like we had to simplify this. So anyways, that ended up as 16. Another way is to use Kenner's theorem, which, by the way, it just says that like 9 in binary, because like we're taking the number of 2's that will cancel out. 9 in binary equals 101, and 18 minus 9 is also 9. And so then Kenner's theorem states that we want to figure out the number of carries when we add this. So there's 1 carry, and then there's another carry. So that's 2 carries. And then basically Kummer's theorem states that that's how many 2's, how many factors of 2, what we call the p-adic value of 2 in 18 choose 9. So basically like in other words, 2 to the 2 divides 18 choose 9, but not 2 to the 3. That does not divide 18 choose 9. You can just look up Kummer's theorem. So anyways, yes, that just ends up with 16. And I think 16 was what we were looking for. The bottom, the p over 2 to the q, and we wanted to find q. So yeah, it's 16. So yeah, any questions?
Okay, thank you, Kennan. Yeah, and thank you, Edward and Alex. And I think, we have done all the 6 problems and providing the solutions. And later, tonight, either tonight or tomorrow morning, I will send the solution menu and also the recording and the problem sheet to you guys. So if you feel like you still have some issues with and understanding like the problems or the answers, then you can look at the solution, the solution manual. In the solution manual, we have the details. And if you have also, if after even look at the solution menu, if you still have any question, you can send us your question, and we can try to find our, instructor to answer the question. Okay. So I think let's call it tonight. Let's call it end. Let's call it, the end. Okay. Bye. Good night, everyone. Yeah.
Bye.
Bye.
Wait, I just have one more question.
Okay, Jay, go ahead, please.
Okay, so it's just sorry, did I zoom in? Okay. So my question is about the rule.
Oh yeah, by the way, here's Kenner's theorem. Oh yeah, continue.
Yes, so 9, okay, yes. So the rule states that 1001, or which is 9 in binary, plus we divided by 1 second, 1, 2, 3, 4, 5, divided by 18. Wait, what does this rule state? Like if you were to put it with variables?
Oh yeah, it's like, wait, what? what was this? Hold on. Okay. So p-adic value, right? It's like
Yes.
yeah. So it basically states that VPN choose n equals if you add n represented in base p plus m minus n in base p, like how many carries you would have. So in this case, n equals 18 and n
Mhm.
equals 9. So p
Mhm.
equals 2, right? So
Yes.
n minus n is 9, which is 1001 in binary.
Yes.
N equals 9, which is also 1001 in binary. So basically, like if you add those two numbers, how many carries? There's obviously 2 carries when you add them.
Mhm.
Like simple arithmetic. So that means VP of hold on, sorry. 2 of 18 choose 9 equals 2. So that basically means we can cancel out a 4 in the denominator. We're basically done because like
Yes.
we
So
have two.
can you like make another example of this formula? I mean,
Sure.
this just an
Like
example. You don't need to solve it.
like 5 choose 3 like v of 5, just saying. Like
And
for
what does V
example,
represent?
p-adic value, like the number, like basically like if you take its prime factorization, like what is the exponent that appears, like v of 5, like 5 choose 3, which is 10. This, well, we know 10 is 2 to the 2
Mhm.
times 5, so we consider the exponent of 5, which is 1. So that means our answer is 1. So basically like that.
Okay. Yes. So in this case, it would be first we would make n into the fifth base plus m minus n.
Second, a binary actually.
Well, in this case, in this problem, it's the fifth base, I think. Like in the
No, it
example.
was, oh yeah. Yeah,
Yes.
5 choose 3.
Plus 2 and we figure out we know what m and n is, and we know what p is. Oh,
Yeah.
okay. Thank you.
Okay.
Bye.
You're
Have a
welcome.
good day.
Bye. Okay. Bye everyone.
Yeah, bye everyone. Bye. Thank you.
Thank you.
Mhm.
I finished.